So we're going to talk a lot in the next couple of days about increasing, decreasing, concavity, and how it all relates to derivatives. So there's this really important test called the first derivative test for extrema. And the test involves critical points. And we've already determined that relative extrema occur at critical points. The behavior around those critical points determines if those critical points are maxes or mins. And I know when we were looking at EVT, I kept saying, all right, we're going to know how to tell if this is a max or a min. We're going to learn how to tell if this is a max or a min without plugging back into the original. And that's what we're doing in lesson 4.3 with the first derivative test. We are determining if something is a max or a min without plugging back in to the original. So it says, given the graph of f below, label the relative extrema. So we can see based on this graph that it is a cubic, and we have two relative extrema. We have a relative extrema here and here. Okay, so what we're going to do is use that previous graph to sketch the graph of the derivative based off what we know from our chart back in the day. So if you recall, we had the chart that was f, f prime, f double prime. And what that chart said was that if the original function is increasing, the derivative is positive. If the original function is decreasing, the derivative is negative. And if the original function has an extrema, the derivative is 0 or DNE, aka what we are calling critical points. And then we had concave up, concave down, and points of inflection. And if it was concave up, then we repeated and it was increasing on our derivative. If it's concave down, it was decreasing. And we had a point of inflection at an extrema. And then if the derivative is increasing, the second derivative is positive. If the derivative is decreasing or the original is concave down, then the second derivative is negative. And if you have a point of inflection, then it's a 0 or DNE. So in terms of our graph over here, to the left of the extrema, it's increasing. And then after our lower extrema, it's increasing again. And in the middle, it's decreasing. So what that tells me is on my derivative, this is positive, then negative, then positive. And if you have an extrema, then it is a 0 on our derivative. So my derivative, or f prime graph, is going to have two zeros, and it's going to go positive, negative, positive. So positive, 0, negative, positive, and 0 in between. The relative min of f prime would become a 0 of its derivative. Where this is decreasing, it would be negative on the next derivative. And where this is increasing, it will be positive. So this graph goes decreasing increasing. So this is 0, negative, positive. So all of that information leads to what we call the first derivative test. So the first derivative test says if f prime changes from positive to negative at x equals c, then f has a local max at x equals c. If f prime changes from negative to positive at c, then f has a local min at c. If f prime does not change sign at c, then f has no local max or min at c. So again, it's important if you're asked to find absolute maxes or just a max of a function on a closed interval, you have to also test those endpoints. That is EVT. So the first derivative test only evaluates the critical points. If you're asked for absolutes, you still have to do the extreme value theorem. So here's our function f of x. And if we want to find where the function increases and decreases, we can do that by looking at the derivative. So we have f prime of x equals 12x cubed minus 12x squared minus 24x. And then we want to find the zeros. So we can take out a 12x. And then factor that. And we get that we have critical points at 0, 2, and negative 1. So those are my critical points. And then now we're going to use our critical points to find increase and decrease. So we're going to take into account the signs of the derivative. So this is a sign chart. A sign chart is not sufficient for justification. So you do have to put into words what the sign chart means on an AP exam. But what we want to do is find what the signs around our critical points are. So I want to know if I plug a number into my derivative less than negative 1, what its sign is. When you plug in, I always tend to plug in right here because I don't care about the actual number. I only care about the sign of the number. So let's say, for example, we're plugging in negative 2. Negative 2 times 12 is negative. I don't care what the number is. It's just negative. So you have a negative. Negative 2 minus 2 is negative. And negative 2 plus 1 is negative. So negative times a negative times a negative is a negative. So to the left of negative 1, the values on f prime of x are negative. From negative 1 to 0, so like negative a half. Plug that in here, you get a negative. Plug that in the middle term, you get a negative. Plug that in over here. Negative 1/2 plus 1 is positive. So a negative times a negative is a positive. Positive times a positive is a positive. Then you have to plug in between 0 and 2. So 1. So you get positive, negative, positive. So that's a negative. Plug in bigger than 2. So 3. Positive, positive, positive. So that's a positive. So what that means is if the derivative goes negative, positive, negative, positive, the original function is decreasing, increasing, decreasing, increasing. So it says find where the graph increases and decreases. It increases where the derivative is positive, so negative 1 to 0, and 2 to infinity. And it decreases where the derivative is negative, so negative infinity to negative 1, and 0 to 2. This first derivative test also shows me where the extrema of the original could be. So negative 1, as you can see, it goes decrease to increase, would be a local min. 0 is a local or relative max. And 2 is a local min, because once again, it goes from decreasing to increasing. Good. So I kind of actually already gave you this information, but it was the next part of the question. So it said find the local max and local mins. This time I did plug back into the original and I found the y values based off of that sign chart. So again, we know that we had our local mins or relative mins at negative 1 and 2. Their y values were 0 and negative 27 respectively. And we had a max at 0, 5. These are not absolutes because this function is increasing in the positive direction. Therefore, you cannot have an absolute max or min. Okay, so let's look at example. Let's look at example 2. Let's find our derivative. Okay, so work out your derivatives super quick and I will be right back. I'm super sorry. So our derivative ends up becoming can't unmute. All right. Our derivative ends up becoming this function here. So you had first times derivative of second plus second times derivative of first. And I'm going to zoom in on this part of the derivative so you can take your minute and check through that. Good. Okay, so check your derivative now. I'm sorry. Okay. So once you have your derivative, you have to find your critical points. The critical points of a function that looks like this, domain and range, are affected by both the numerator and the denominator. So the numerator is going to give you the derivative points that are 0. The denominator is going to give you the derivative points that do not exist. So what we have to do, and this is kind of why I created that common denominator, is we have to set both the numerator and denominator equal to 0 to find the critical points of both. So you set negative 2x squared plus 4 equal to 0, and you get x equals plus or minus the square root of 2. And then we also have to set our denominator equal to 0, and we get x equals plus or minus 2. And again, those denominator points are the points at which f prime of x does not exist. And these are the points at which f prime of x equals 0. Both of these are critical points of interest to us. The reason I took into account our domain is that we can't use something outside of the domain in our first derivative test. So we know that by definition, a square root cannot have negatives underneath it. So we know that we can't have any values of which x squared is going to be greater than 4. So that limits and restricts my domain to negative 2 to 2. It does include those 2 points though. So when I get my critical points down here at positive and negative 2, they're included because positive and negative 2 are included on my original function's domain. So what we do is perform our first derivative test again. So what I'm going to do is plug in values to the left and to the right of my critical points. So let's do that together. So here's my sine line. I have negative 2, negative root 2, positive root 2, and positive 2. And again, I don't care about the values to the left or right of negative 2 and positive 2 because they're not in my domain. So I need to look at the values between negative 2 and negative root 2, between negative root 2 and 2 and root 2, and between root 2 and 2. The easiest one of these is obviously plugging in 0 here. Remember, we're plugging into my derivative, which is right here. So 0 squared is 0. So on top you have a positive. On the bottom you have a square root, where you can only get a positive number from a square root, because again, you can't take the square root of a negative. So in the case of this problem, my denominator is always going to be positive. So I have a positive over a positive, which is a positive. We talked about the square root of 2 the other day. So we know that the square root of 2 is greater than 1, because the square root of 1 is 1, but it's smaller than 2. So the tricky part is knowing what you can plug in here. My suggestion is always to get as close as possible to the endpoint you do know. So I'm going to pick negative 2 or negative 1.9 to plug in. So if you plug in a negative number and you square it, it's always positive. So negative number squared is always positive. So this is a negative 2 times a positive almost 1.9 squared. It's kind of like 2 squared, which is 4. So this number is going to be kind of close to 4, so like 3.8-ish, etc. So that tells me that negative 2 times a number near 4 is like negative 8, which is greater than 4. So that tells me my top is negative, bottom's always positive. So this is negative. Same thing's going to happen over here, because negative 1.9 and positive 1.9 squared are the same. So I know that my derivative gives negative, positive, negative. So for part A, it said, where are we increasing and decreasing? So we are increasing from negative root 2 to root 2. And we don't include our endpoints because those are critical points. They're not really in the intervals of increase or decrease. And then it's decreasing. Now you can include this endpoint because it's a hard domain. So negative 2 to negative root 2. If you didn't include the endpoint, that's also fine. So that's one of those weird ones where they would accept a hard or soft endpoint inclusion. So you could have a bracket or a parenthesis. And same with on the other side. You could have root 2 and then to 2. Now I always suggest if you do a bracket the first time, you do a bracket the second time. If you used a parenthesis the first time, to use a parenthesis the second time. And then local max and mins. Well, we can see here that if this is going down and then up and then down, we have a min at negative root 2 and we have a max at positive root 2. So again, relative min at negative and a relative max at positive. And we are going to stop there for today. Your homework is in the textbook. So I'm just going to give you 6 problems. So you're going to page 215. You're doing 1 to 6.